Thank you for having me here. It's a pleasure to be online today to talk about my work in the East African Rift. What I'm going to talk about today is a brief overview of over 7 years of work in Ethiopia. I won't have time to touch on what I've been doing in the Turkana region of Kenya for sake of time. I'm happy to take questions later. Most of this work has been in collaboration with at least 20 colleagues from all over the world, which I acknowledge. I'm not crowding the slide with names, but I want to acknowledge their contribution. So I will talk about volcanoes, the ash they produce, and I might refer to what we call TUF or TEFRA during this talk. So if you're unfamiliar with the jargon, TUF or TEFRA broadly refers to volcanic ash. I will also talk about how ash is used traditionally and by scientists in the Rift. So let's dive in. Here is possibly a familiar photo of the mythical African Rift Valley. It is, of course, famous for being a critical region to understand human evolution. Among the many fossils discovered in this region stand the two oldest Homo sapiens specimens known so far, retrieved in the Kibish and South Afar regions of Ethiopia. A lot of the research in the region has aimed to understand speciation, migration, habitat, environment, and climate in which our ancestors lived. But until recently, little attention had been paid to volcanism. When we consider the numerous volcanic systems across the rift represented here as red triangles, we cannot help but think about how our ancestors lived with volcanoes and how have volcanoes played a role in shaping the habitability of the rift. So some of my work has focused on the volcanic record in Ethiopia during the Middle and Late Pleistocene, more specifically in the range of 500 to 50,000 years ago. To understand why volcanism occurs in the rift, we can look at the geological setting of the region, which many of you will be familiar with. Black arrows on the map on the left indicate the movement of plates apart from each other, which thins the lithosphere and enhances magma production. And that results in volcanic activity in the Rift Valley that evolves from flood basalt, which you see in the bottom diagram E on the right-hand side, on the onset of the rift formation, and evolves into strings of volcanoes that follow the rift axis as depicted on the diagram C, a bit higher up. A focus of our research has been large volcanic systems and calderas in Ethiopia, which is suggested to comprise around 60 volcanoes that were active during the Holocene. And several studies suggested that the caldera forming events, so the largest eruptions, would have occurred during the Pleistocene, a period which is, of course, relevant to understand human evolution in the region. But until recently, we knew very little about these giant eruptions. So that's a close-up map of the Ethiopian Rift and volcanic system in orange triangles. And if we zoom in, we can look at the central region of the main Ethiopian Rift, where we find about a dozen calderas. And in order to constrain the timing of these eruptions and their chemical fingerprint, we analyzed the deposits of the caldera-forming eruptions using argon-argon dating, as well as geochemical analysis. What we found was that all those large magnitude eruptions occurred between around 300 and 70,000 years ago, and very likely blanketed the landscape with ash over hundreds of kilometers. So again, bearing in mind that this time frame covers the period in which our ancestors lived in the rift, according to the ages of the oldest fossils of Homo sapiens found south of the rift and north of the rift, represented here on the map. So going back to some basics, because I was informed that I had to make sure just to be mindful of not everyone had the background. So the characteristic of explosive eruptions is to produce ash, ash plumes of variable height. The more explosive, the higher, and as a result of a process of fragmentation of the magma in the conduit. This is a process that generates what is called tephra, ranging from large permeability clasts to very fine ash. And these eruptions can go on for hours to tens of hours, and the intense flux of energy propels the ash to great heights, typically reaching the stratosphere. The ash then falls at the surface following the direction of main winds, and therefore we can find it over large distances away from the source volcanoes. Geologically speaking, the deposition forms rapidly a layer that will soon be covered by other sediments, sealing a horizontal time marker, which can be found at several sites from close to far away from the volcanic source. And I'll come back to that in a minute. First, I would like to talk about what I've come to discover during my fieldwork, is that volcanic ash has long been used traditionally by local communities in various ways. West of Lake Turkana in Kenya, medicine men have prescribed covering one's skin with ash against all sorts of ailments, including high fever, but also to dispel anyone from a difficult situation. This has been very helpful in the field in our research, because local people have been able to show us where ash layers can be found because they use it. I later found in my research that volcanic ash has been used in Europe as an homeopathic remedy since 1869, using Icelandic volcanic product, which can be ordered online. That was just a short digression. Beyond medical purposes, it's been known for a while now that volcanic ash is used as ornament in the rift, a body ornament. It can be mixed with colored clays and or with wood ash. This mixture is used to enhance beauty for spiritual purposes in ceremony, but also commonly to indicate someone's age group. We know also that some specific colors and patterns have been used by warriors to intimidate enemies. But most importantly, body makeup is used to denote tribal uniqueness, for which the Karo tribe of the Omo River, depicted here on the photos, is probably one of the most famous examples. Back to my work, and now, of course, for scientists, volcanic ash is used to date sedimentary environments, which is also referred to as tephrochronology. So I'm going to use this word a lot. So I've decided I'll do a 1-minute crash course of tephrochronology for those who are unfamiliar with how it works. So it relies on the fact that, as I mentioned before, those explosive volcanic products might be produced and travel over a month to years, but on a geological timescale, land nearly instantaneously. And they set a defined stratigraphic time marker if it is preserved from post-deposition process. Depending on the grain size, ash can travel large distances and blanket the landscape. In theory, each eruption has a unique geochemical fingerprint, which is a record of the magma journey towards the surface. But in practice, it's a bit more complicated, as I will explain later on. So tephrology consists in linking tephra from different sites and all to their volcanic source. They therefore provide a time marker for a paleo environment, as well as track the dispersal of an ash cloud. This correlation can be limited by several factors, including the size of the ash grains or shards, which can preclude argon-argon dating, or the analysis of some elements in trace concentration. Another issue might be the degree of alteration of a deposit, which might affect the concentration of certain geochemical elements. Finally, in some regions of the world, eruption might not be dated or deposits might not be analyzed. So in the East African Rift, in particular in Africa, it's been a key in Ethiopia, it's been a key tool to link archaeological sites together with a known tephra and or its source eruption, therefore providing relative ages for archaeological assemblages as well as fossils. As an example, we can have a look at the map on the left, where the Pleistocene archaeological sites in Ethiopia are reported in boxes. At all these sites, tephra layers frame fossils or artifact-rich sediments. The Chobahar sediments in the south are from a core extracted from a paleo lake of the same name. Having reconstructed the timeline of large eruption in the Ethiopian Rift, the next task was to explore potential correlation between proximal deposit of this eruption and tephra from distal sites, such as at Kibish or Konso Gademota or Herto, which you can see the synthetic or the crop selected stratigraphies on the right-hand side with the tephra layers reported in green. So let's explore an example. I'm not going to go through everything. There's a lot of chemistry over there, lots of plots, and not very good at this time of the day, probably, to digest. So I'm just going to look through one example. So for many years, about 20 years, colleagues have attempted to better constrain the age of the two Homo sapiens fossils from Kibish and Herto in Ethiopia by analyzing and correlating hash horizons found at these sites, since none of these could be dated directly using argon-argon, the argon-argon technique. It has been argued that even both fossils were lying under the same tephra layer, namely at Kibish, so on the left column, but under the KHS tuff, and at Herto under the WAVT tuff on the right-hand side of the diagram. However, these correlations were quite uncertain because the data sets that were compared were acquired using different analytical conditions and were limited to a certain number of chemical elements. So what we did is that we resampled tephra of interest and we analyzed their composition in the same analytical condition. And we compared with the composition of proximal deposit we had analyzed previously. In practice, what it looks like, that's an excerpt. So I just use 4 diagrams to show you. So we use biplots of elements or element ratios, including major oxides and trace elements that are characteristic of volcanic ash. When 2 populations overlap on all biplots, we consider a correlation to be likely. And what is complicated in this particular region, as well as in other regions of the world, from what I understand, is that volcanoes can produce geochemically very similar ash layers within a large geographical areas and over several tens of thousands of years. So the number of elements we can use to discriminate a layer from another are limited. Now, this work has allowed us to link clusters of distal ash layer with dated eruptions, therefore improving the chronology of these sites. What you see here, there's 2 main clusters. One, if you look at the top left diagram, a cluster with in blue the KHS stuff, which cover the Homo-1 deposits, is linked to the Shala eruption, dated 233,000 years. And there's another cluster linked to the 177,000 years eruption of Kobeti.
Okay, Céline, that's 10 minutes.
Okay, thank you. Yeah, 3 more slides. So these correlations show that the 2 oldest known Homo sapiens in East Africa are not lying under the same tephra layer or horizon as suggested previously. Instead, we found that the KHS stuff on the left-hand side in blue is a distal correlative of that Shala eruption, and it is above the Homo-1 fossil, and therefore that refines its minimum age to be around 230,000 years, whereas before it was estimated to be younger than 195,000 years. That also confirms that the Herto hominins on the right-hand side are possibly much younger than Homo-1. So our work also discarded previous correlation with other tephra layer with the other formations that we see here in the middle. I'm not showing all the diagrams, but the story is much more complex than the initial broad correlation there was between all those sites. When we take into account all the other correlations we've made, we've published a revised stratigraphic framework for the formations in the Ethiopian Rift. This is what you can see here. If you want to have a closer look, it's in our paper published 2 years ago in Quaternary Science Reviews. And one of the work we've done in the Chobaha core as well is that we've been able to correlate tephra horizon with some of the dated eruptions, and that helped us to, it contributed to build the age model for that record, and we're still looking at cryptotephra, so tephra that is not visible in the core, to identify other eruption in that record. This record, the sediment record, has recently it's been published last year, enabled the whole group to reconstruct the climate viability in this region. So I'm gonna just, what we're doing now is that we're focusing on the relationship between the Herto tuffs with the Herto tephra with proximal deposits in the Ethiopian Rift, as well as working on that core. Overall, our efforts aim to develop a tephrochronological framework for that region that will help addressing a range of interrelated questions, including volcanology, paleo environment, and paleoanthropological. And I'll stop there, and I hope I'm still on time. Yes.
Thanks very much. So are there any questions from the audience? If you just raise your hand. Yeah, there's a hand. Who's that? Okay, I can't see who's got to raise their hand, but just unmute yourself and ask the question.
Excuse me, how do we raise the hand on this?
I'm not sure. Okay. Do you have a question?
Yes, I have
Hey, just go for it.
Okay. So, hello. So I'm Hugo Albared. I'm a PhD student from University of Bordeaux in France. And my question would be, for instance, if we have a volcanic eruption, so we would have a proximal deposit with a given composition in major and trace elements. And let's say if we have a distal or ultra distal deposit of that same eruption, would it be possible to have the same major element composition but a different trace element composition? I don't know if it's possible in terms of petrological or volcanological processes, maybe different eruption phase, or I have no idea, but would it be possible according to you to...
Yeah, thank you, Hugo. It's a good question, and it's not the straightforward answer is a correlation means that the both major and trace suites of composition should be the same within a certain statistical range. Now, what might happen is if you have, and we see that for very big eruptions, proximal deposit, you might just find a part of the eruption if another part has been eroded. And in the distal deposit, you find other phases of the eruption which proximally have been eroded, or vice versa. And so that might track. So, for example, when a very large magma reservoir is emptied in a very big eruption, there might be different degrees of composition that might be recorded only in distal layers that are better preserved, depending in whatever records is best preserved. In theory, if it's it should be the same, but there must be some indicator that there is at least there's a same suite, or at least a population of the grains you analyze that is exactly the same.
Yeah. Thank you.
You're welcome.
Yeah. So we've got one more question from Adele Mustafa. If you want to go for it.
Yes, please. Does every volcanic eruption produce ash?
Only those who would be explosive, Adele.
Okay.
So eruptions effusive in nature would produce more lava, or what we call scoria. Yeah.
Thank you.